In the following lecture, we're going to discuss the electrochemical cell, which is also known as a Voltaic cell or a Galvanic cell. We're going to discuss this in the simplest possible terms because this is for junior students. A simple electrochemical cell is made up of two metals that are going to have different reactivity. And how would we figure out the reactivity of these metals? We're going to discuss briefly the reactivity series. And if you remember the reactivity series, this here is the reactivity series. I've written it down. The metals on the left hand side are the more reactive metals, and the metals on the right hand side are the less reactive metals. So as you move from left to right, the reactivity of metals decreases. Group 1 metals like potassium, sodium, or group 2 metals, calcium, they are very reactive, whereas metals like transition metals, platinum, gold, silver are very unreactive. We also need to understand the meaning of the term reactivity when it comes to metals. So if we say that a metal is very reactive, that means that it has a very high tendency to lose electrons. So it's going to lose electrons very easily. For example, you have potassium. Potassium is very reactive. That means that potassium has a very high tendency to form potassium ions, and it's going to lose its outermost electrons very, very easily. On the other hand, if you have metals that have very less reactivity, like platinum, like gold, like silver, that means that they don't tend to lose electrons very easily. For example, silver, it would be very hard for silver to actually form silver ions and lose electrons. So this is not going to be very spontaneous or not possible in the case of silver. Silver doesn't like to lose electrons. Now I've drawn over here a very simple electrochemical cell or voltaic cell. And the cell consists of two metals that are connected together. One is zinc and the other one is copper. Now, between these two, zinc, if you look at the reactivity series, zinc is higher up in the reactivity series compared to copper. Copper is less reactive, whereas zinc is more reactive. So this metal over here, this zinc metal that is the left-hand electrode, this is called your electrode. This is the more reactive side, more reactive metal. And the other metal on the right hand side, which is copper, is your less reactive metal. Now the rule is, when you connect two metals together, the rule is that electrons would tend to flow from the more reactive metal to the less reactive metal. The reason why that's going to happen is, why electrons are going to flow from the more reactive metal to the less reactive metal, is that we have discussed before, that the more reactive metal would tend to lose electrons easily, which means that zinc over here is your more reactive metal. So zinc is going to have a very high tendency to lose electrons, and when it loses electrons, those electrons are going to accumulate on the electrode, and a lot of zinc ions would be produced in the solution. So the solution would start there would be a lot of zinc ions being produced in the solution, because all the zinc metal would be converted into zinc 2+ ions, and it would start losing electrons. So a lot of electrons would accumulate. Copper, on the other hand, is less reactive, which means it doesn't have a very high tendency to lose electrons. So what's going to happen is that all these electrons that are accumulating over here would eventually start traveling to the other side, because all these electrons are going to start repelling each other, and they're going to be pushed to the other side towards the copper electrode. Now once these electrons, they all start reaching the copper electrode, they need a place to go somewhere. So these electrons, because copper metals don't gain electrons, they don't form negative ions. So when these electrons, they reach this electrode, you need an electrolyte in the solution. For example, if the solution contains copper 2+ ions, an electrolyte is a solution that contains ions, because ions are able to gain or lose electrons, and they're able to conduct electricity. So you need an electrolyte in the solution. So if the solution contains copper 2+ ions, and all these electrons are coming in from zinc is the one that's losing electrons, and all those electrons start flowing towards copper. The reason because copper is not producing electrons, and once they reach copper electrode, these electrons would be gained by the copper ions in the solution. All these electrons would be gained by the copper ions in the solution, and a reaction is going to take place at the copper electrode, which is that copper ions would start gaining electrons to form copper metal. And in this way, current flow would be possible. Zinc, the more reactive metal, would be losing electrons, producing all these electrons. Those electrons would start traveling to the other side, where copper ions in the solution would start gaining those electrons and they would be reduced. So what's happening at the zinc electrode is called oxidation, because it's losing electrons. Loss of electrons is oxidation. And what's happening at the copper electrode is reduction, where copper ions are gaining those electrons back. And this is how a current flow is generated in an external circuit. Now, one other important aspect of this electrochemical cell is this salt bridge. And salt bridge is very necessary because it provides an electrical contact between the two electrolytes. The reason why an electrical contact is necessary is that, as you can see over here, oxidation is taking place. So zinc is very quickly turning into zinc 2 plus ions. So the quantity of zinc 2 plus ions in solution is increasing. So there would be a lot of positive ions increasing in quantity. More positive ions are being produced. On the other hand, these electrons travel to the other side, where the copper ions in the solution get converted into copper, which means that positive ions in the solution actually start decreasing. So on one side, your solution is becoming less positively charged because all the positive ions are decreasing. On the other side, this solution over here is increasing in positive charge because the positive ions are increasing. So the salt bridge creates a sort of connection between the two electrolytes, and it helps to stabilize the amount of ions present in solution. It doesn't let the charges build up. The positive ions are going to diffuse into the salt bridge. From the other side, the positive ions would diffuse out of the salt bridge, so that the positive ions do not decrease, they increase. So to stop this from happening and to provide an electrical contact between the two solutions, a salt bridge is very necessary. Another very important point about this electrochemical cell is that the greater the difference in reactivity of metals, it's going to lead to more voltage and more current. What that means is that in this electrochemical cell we used zinc and copper, but if we had used metals that had greater difference in reactivity, for example, if you look at the reactivity series, if we had picked silver and magnesium, the difference in reactivity between silver and magnesium is much greater. So the amount of electron flow and the amount of voltage created by that electrochemical cell would be much greater. So the greater the difference in the reactivity of the two metals, the greater the voltage that is produced. Here is another example of an electrochemical cell. The diagram is slightly different, but the functioning is going to be exactly the same. In this electrochemical cell, you have magnesium metal and silver metal. Now, magnesium is the more reactive metal, so this is your more reactive metal, because in the reactivity series, magnesium is right at the top, silver is almost at the bottom. So magnesium is your more reactive metal, which basically means that magnesium has a very high tendency to lose electrons. So the reaction that would be happening at the left-hand electrode would be that magnesium would be losing electrons to form Mg2+, and it would be producing 2 electrons. So over here in the solution, the amount of Mg2+ ions would gradually increase because a lot of magnesium would be converted to Mg2+, and a lot of electrons would be lost. These electrons would accumulate at this electrode. Mg would, because it's more reactive, would quickly convert into Mg2+ and lose a lot of electrons. And where would these electrons go? They would slowly start traveling to the other side, towards the silver electrode. Silver is your less reactive electrode, which means silver atoms don't have a very high tendency to lose electrons. So these electrons would travel to this electrode, where somebody has to gain these electrons. Mg is the one that's losing electrons. So it's losing electrons, it's producing a lot of electrons, and those electrons travel to the other side, where you have a sulfuric acid electrolyte. Now, in sulfuric acid electrolyte, you have a lot of hydrogen ions in the solution, H+1 ions. And these H+1 ions would attract electrons. So those electrons coming from magnesium would eventually be attracted by the hydrogen ions in the solution. So these H+1 ions would start gaining electrons, and when they gain electrons, they would start forming hydrogen, and hydrogen is diatomic, so H2 gas would be formed. on the right hand electrode. So Mg and silver were the two electrodes connected together, but Mg was the more reactive, so it started producing electrons and started getting converted into Mg2 plus ions. Those electrons started traveling to the other side, where the electrolyte containing H plus 1 ions, those electrons eventually were gained by H plus 1 ions, and those H plus 1 ions got converted to hydrogen gas. So what you're going to notice at this right hand electrode are going to be bubbles of hydrogen gas forming. Another thing that you would notice is that on the left hand terminal oxidation is happening, on the right hand terminal reduction is happening. There's a gain of electrons taking place at the right hand terminal, and there's a loss of electrons taking place at the left hand terminal. Now remember, in electrochemistry, wherever oxidation occurs, that's your anode. So this left hand terminal is your anode, and wherever reduction occurs, that's going to be your cathode. You would also like to notice that the terminals, which one is positive and which one is negative. Because magnesium was producing a lot of electrons are accumulating on this left-hand terminal. So this is going to have negative polarity. A lot of negative charge would be built up, and no one was losing electrons on the other side. So electrons were traveling to the other side. So this would be relatively a positive terminal. So electrons were traveling from where they were being produced, where they were more in quantity, and they were traveling to the place where they were less in quantity, or from the more reactive metal to the less reactive metal. So remember, wherever oxidation occurs, that's your anode, and wherever reduction occurs, that's your cathode. I am now going to try and do a few example questions. For example, this question taken from a GCE paper states that in which circuit does the bulb light? So there are 4 electrochemical cells drawn, and I need to figure out in which circuit would there be a flow of current and the bulb. This here symbol represents the bulb. In which circuit would the bulb light? Now remember, for example, if you look at the first option, there's copper metal on this side and there's copper electrode on the other side. Remember, for an electrochemical cell, the two metals should have a difference in reactivity. If there is no difference in reactivity, which means that there would be no electron flow. So this first electrochemical cell would not produce any current. If you look at this other electrode over here, you have a silver metal and you have a zinc metal on the other side. Zinc is the more reactive metal. So zinc would lose electrons very quickly, very easily, and those electrons would eventually flow to the other side. But the problem is that the solution does not contain an electrolyte. It contains NaCl solid. Remember, if zinc, because it's more reactive, starts to lose electrons, and if it starts to produce electrons, those electrons would accumulate on the zinc electrode and they would try to go to the other side. But on the other side, if the solution contains no aqueous ions, then there would be no place for the electrons to go. So if you want electrons to flow, you need ions in the solution that are able to gain electrons from the other side. So there's a net flow of electrons. So in this case, there would be no flow of electrons because there's an electrolyte absent. Electrolytes are acids, bases, or salts in aqueous state, in dissociated state. Similarly, if you look at this option C, again you have zinc metal and copper metal. Zinc is the more reactive metal, so there is a difference in reactivity. Zinc would produce electrons. The electrons would try to go to the other side, but the problem again is that this is not an electrolyte. You need dissociated aqueous ions in the solution, so that if zinc starts producing electrons, because it's more reactive, those electrons reach the other side and somebody on the other side is able to gain electrons. Only then would a flow of current be possible. Let's discuss this last option, which is option D, and option D is the correct option because over here the bulb that is drawn is going to light up. You have copper and silver. Between copper and silver, copper is more reactive, so copper would start to lose electrons and it would start producing copper ions, and 2 electrons would be lost. Those electrons would accumulate and eventually they would start to flow to the other side, which is the silver electrode, which is the less reactive electrode. But the solution now contains H2SO4 aqueous, which means that there are a lot of H plus 1 ions in solution in dissociated state. So eventually, when these electrons reach the other side, there's somebody on the other side that's capable of gaining those electrons, which in this case are hydrogen ions. They would gain electrons and they would start forming hydrogen. gas. So in this case, electron flow would be possible. Copper being more reactive would start losing electrons. Those electrons would travel to the other side, where H+1 ions in the electrolyte would start gaining electrons, and there would be a net flow of electrons in the external circuit, and this bulb is going to light up. Here's another example question. In this question, again, there's an electrochemical cell drawn where you have magnesium metal which is connected to a copper metal, and there's an electrolyte present which is magnesium sulfate, and it should probably be in aqueous state, dissociated state, and there are electrons flowing. The question is, explain why the flow of electrons is in the direction shown in the diagram. Now, if you look at the two metals, you have magnesium and you have copper. Remember, magnesium, if you look at the reactivity series, is the more reactive metal, which means that magnesium would lose electrons quickly compared to more easily compared to copper. So it's going to start producing all these electrons, and when it loses those electrons are going to accumulate on the electrode, and they would eventually start flowing to the other side where there would be lesser electrons. So the answer to the question, explain why the flow of electrons is in the direction shown. So remember, the answer is that electrons in an electrochemical cell flow from the more reactive metal to the less reactive metal. So since it's a 2-mark question, we also need to probably describe which one is the more reactive metal, which in this case, more reactive metal would be, it's going to be Mg, and the less reactive metal would be, in this particular case, it's going to be copper. Here's another example question, and this time another Voltaic cell is drawn, where one side you have zinc electrode, the other side has iron electrode, and there's sulfuric acid in the solution, so there's an electrolyte present in the solution. Now the question stated, which substance in this cell is the reductant and which ion is the oxidant? Now first there is iron and zinc. You have to figure out which one is the more reactive. If you look at the reactivity series, zinc is the more reactive electrode. So since it's more reactive, it's going to have a higher tendency to lose electrons. So on the left hand electrode, what's going to happen is that zinc metal would start losing electrons, or would start producing electrons. So all these electrons are going to accumulate on this electrode, and they are going to eventually travel to the other side from the more reactive to the, so this is the more reactive metal, and the electrons are going to be produced by the more reactive metal, and they're going to be traveling to the less reactive metal. Now if you look at the equation on the left hand side, this equation is an oxidation equation, which means that zinc is a reducing agent or a reductant. Remember, whichever substance is getting oxidized, that is the reducing agent or the reductant. So which substance is a reductant? That's going to be zinc, because it's undergoing oxidation. Now all those electrons are going to travel to the other side. Zinc is producing electrons. Those electrons are going to travel to the other side, to the less reactive metal. Remember, metals don't gain electrons, they don't form negative ions, so those electrons are going to travel, and the solution contains sulfuric acid, so there is a lot of H+1 ions in solution, and those electrons would travel and they would eventually be gained by this ion in the solution, which is H+1. So H+1 ions would be gaining electrons to form hydrogen gas, so which is why you're going to see bubbles of hydrogen gas forming over here. So zinc, being more reactive, produces all these electrons, and those electrons travel to the other side, and in the solution H+1 ions are the ones that are gaining those electrons. So which means that H+1 ions are getting reduced. So reduction is happening, and whichever substance gets reduced, that's the oxidizing agent or the oxidant. So the oxidant in this case is going to be H+1 ion. The last part of the question is, how could the voltage of the cell be increased? Now, there are two ways of increasing the voltage, and we have discussed this as well. If there's more difference in reactivity of the electrodes, there's going to be more voltage. So instead of using zinc, use a more reactive. So instead of zinc, remove zinc, change zinc to magnesium electrode. So if you do that, the difference in reactivity, magnesium is even more reactive, so more electrons are going to be produced. If you use magnesium electrode as the left-hand electrode, so more electrons are going to be produced, and those electrons would travel to the other side and more voltage would be produced. So you either change the zinc electrode to magnesium electrode. There are some other things that you could do. You could also increase the concentration of the electrolyte. So increase concentration of H2SO4. Remember, these square brackets, they stand for concentration. So that's another way, because if you have more H+1 ions in the electrolyte, then the amount of electrons gained by this would increase. So more electrons would be able to move from the left to the right hand electrode and would be gained by H+1 ions. So if you increase the amount of H+1 ions in solution, or increase the concentration of sulfuric acid, that's another way of increasing the voltage of the cell.